Okay, so now we want to go through our steps, apply our rules, and draw some actual Lewis structures for molecules. So for the molecules, we're going to show what's actually happening with their bonding and with their electrons. So we'll go through the examples that are typed out in your notes. So the first example is a molecule formed by fluorine and fluorine, so a bond between two fluorine atoms. So let's go through our steps. The first step is to find the number and type of atom involved. So we have two fluorines here, so that's pretty easy. The second is to find the total number of valence electrons. So go to the periodic table, find fluorine, it's in group 7A. So each fluorine has 7 valence electrons. So I have 14 electrons to work with. The third step is to write out the skeleton structure for the molecule. So here we don't have to worry about deciding on a central atom because there is no middle here. I just have 2 atoms that are going to be bonded together. So we can put them side by side. So then I go ahead and connect them with one bond. So when I draw the skeletal structure, I connect everything. So if you drew it vertically, it wouldn't be wrong, but we typically go horizontal here. So I've already used 2 electrons. Okay. So now I only have 12 valence electrons left. So now I go and I place the electrons around the atom. So if I have 12, I'll put 6 around each fluorine. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So now I go back and I check 2 things. First, I check that I actually used 14 electrons. So there are 2, 4, 6, 8, 10, 12, 14. I'm good there. Then I make sure that each atom has a full octet. So it has 8 valence electrons. So let's do that. Let's check the fluorine on the right first. It has 1, 2, 3, 4, 5, 6. And then it's sharing these 2 electrons, so I count them both. 7, 8. Then this fluorine has 1, 2, 3, 4, 5, 6. Then it's sharing these 2, so 7, 8. So we're good. We double check, so this is the correct Lewis structure for fluorine. So when 2 fluorine atoms bond together, so when you have diatomic fluorine, so that would be the chemical formula F2, you see that 1 pair of electrons is being shared, and that each atom has 3 lone pairs of electrons. So 3 lone pairs is 6 valence electrons that aren't being involved in bonds there. Okay, so let's look at the next one. H and Cl. Okay, so the number and type of atom is pretty self-explanatory here. I have a hydrogen and a chlorine. Okay. So then I need to find the total number of valence electrons I have present. So hydrogen's 1A, so 1 plus chlorine 7A plus 7 equals 8 electrons. So I have the skeletal structure. So I already used 2 electrons. So I have 6 electrons. So now I have 6 more electrons I have to place. But I can't really put 3. We always want to put electrons in pairs, so I can't put 3 around each of these. But remember, hydrogen only wants 2 electrons. So H only needs 2 electrons. That's because hydrogen only has the first energy level. So it has 1s1 or 1s2. So it already has 1 electron, so I put the second one in and now it's full. So now because hydrogen is sharing these 2 electrons, it has a full energy level, 1s2. So I can put all 6 around chlorine. Okay. So now I go back and double check myself. I used 1, 2, 3, 4, 5, 6, 7, 8 electrons total, so I'm good there. Hydrogen has 1, 2 electrons, so it's happy. Chlorine has 1, 2, 3, 4, 5, 6, 7, 8 electrons, so it's happy. So that's my final answer. Okay. So now let's go ahead and look at CH3I. So I know I skipped a couple in the notes. You can go back and try BR and BR and I on your own. So this is a more accurate way of showing that we have a molecule here. Instead of writing chlorine and hydrogen, we show the actual chemical formula here. So the first step, determine the number and type of atoms. So I have 1 carbon, 3 hydrogens, 1 iodine. So add up the number of valence electrons. Carbon has 4, each hydrogen has 1. Then iodine has 7, so that's 14. So I have 14 electrons total. Then I need to write the skeletal arrangement. This one's a little more complex though, because I can't put a simple linear arrangement here. Something has to be in the middle. Okay, I could do it linear, but typically if there's more than 3 atoms, we don't have a linear arrangement. So I'll think about my rules for what is my central atom, what goes in the middle. So I remember that if I have carbon, carbon is typically my central atom. So I start off by putting carbon in the center. So then I arrange the other elements around carbon. So if I did this, or if I did this, those are the exact same thing. Okay? You can rotate the molecule and you still have the exact same answer. Okay? So now I connect the atoms. So everything's going to be connected to the central atom here. So now I use 2, 4, 6, 8 electrons already. So 14 minus 8 is 6. So I only have 6 electrons left over that I can use. So I need to decide where I'm going to put them. So hydrogen's already good. This hydrogen has 2 electrons already, this has 2 electrons already, this has 2 electrons already. So they're already happy. This carbon already has 8 electrons. It has 2, 4, 6, 8. So the carbon's already good. Iodine is not, however. So I put these 6 electrons around iodine. Okay, so now I go back and do some double checking. First, I make sure that I use the correct number of electrons. So I use 2, 4, 6, 8, 10, 12. I used 14 electrons, so that's good. Now make sure everything's happy. Hydrogen has 2, 2, 2. We're good. Carbon has 2, 4, 6, 8, so we're good. This iodine has 2, 4, 6, 8, so everybody's happy here. So this is my answer for the Lewis dot structure for CH3I. Notice I could have also put this answer, and it's the exact same thing. Okay, so you can rotate the molecule around and it makes no difference. As long as you have it connected the same way and the electrons in the correct place, you can shift it however you want to. So let's look at another one. NH3. So the number and type of atoms, I have 3 nitrogens, or excuse me, I apologize, 1 nitrogen and 3 hydrogens. So determine the number of valence electrons. So nitrogen has 5 plus 1 plus 1 plus 1. So I get a total of 8. So now I'll look at the atoms and try to determine the central atom here. So I know that hydrogen can't go in the center. So nitrogen has to be the central atom, and I have to have the hydrogens around the nitrogen. Okay. So I can also have this. Okay, so whatever how you want to arrange it there, that's perfectly okay. So then I need to connect to them. So connect everything to the central atom. So I'll just show 2 different correct answers here. So look, I already used 2, 4, 6 electrons. So I only have 2 electrons left I need to place. So hydrogen is already good. Hydrogen has 2, hydrogen has 2, hydrogen has 2. So the dots need to go on the nitrogen. So I put 2 electrons on nitrogen. Okay. So let's go back and double check. In total, I used 2, 4, 6, 8 electrons, so that's good. Each hydrogen has 2 electrons, and nitrogen has 1, 2, 4, 6, 8 electrons, so everybody's happy. So both of these answers are equivalent, so they are both perfectly valid answers here. So either one of these are correct for the Lewis dot structure for nitrogen. So I could ask you some questions about this. Nitrogen has 3 single covalent bonds, and it has 1 lone pair of electrons, but it has 2 electrons on it. Okay, so they could be asking different ways about the number of pairs or the number of electrons. So let's go ahead and let's look at SiF4 together. Okay. So the number and type of atoms here, 1 silicon, 4 fluorines. So I add the number of valence electrons up. So silicon has 4 plus, and I'll go ahead and say 4 times 7 because each fluorine has 7 valence electrons and there's 4 of them. So then I add up the total. So I have 28 plus 4, so I have 32 electrons. So that's a lot to deal with here. So then for the central atom, I choose the least electronegative element. So if I compare silicon and fluorine, I see that silicon is the least electronegative. So silicon goes in the middle. The fluorines go around it. Okay. So then I go ahead and I connect them. Okay. So now don't forget to go back and count up how many electrons I already used here. So I already used 2 electrons for each bond here. So I need to go back and say 2, 4, 6, 8 electrons got used. So I say 32 electrons minus 8, and I get 24 electrons left over. So silicon already has 2, 4, 6, 8 electrons. So I'm in good shape there. So I have 4 fluorines. So in order to evenly divide up 24 electrons between 4 atoms, they each get 6. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 2, 3, 4, 5, 6. Okay? So now I use 24 electrons. So let's go back and double check. Make sure first I use the correct total number. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. So I used 32 total, so I'm good. Now let's check for each atom. So silicon has 2, 4, 6, 8 electrons, so it's good. And every fluorine has 2, 4, 6, 8 electrons, so all the fluorines are good. Okay? So that is the correct Lewis structure for silicon tetrafluoride there. So let's look at a few more together. Let's look at H2S. Okay. So same basic process we've used the whole time here. 2 hydrogens, 1 sulfur. So I have 1 plus 6 valence electrons. So I have 8. Hydrogen's never the central atom, so sulfur goes in the center. So I have a hydrogen on each side. I just used 2 4 electrons, so minus 4 electrons. So I have 4 left over. Hydrogen doesn't need them. Hydrogen will never have lone pair electrons. So I put the 4 on the sulfur. I go back and double check my work. I have 2, 4, 6, 8. That's correct. Sulfur. 1, 2, 3, 4, 5, 6, 7, 8. So I'm good. Hydrogen 1, 2. Hydrogen 1, 2. So I'm in good shape. There's the Lewis structure for H2S. Okay. So I know I skipped around a couple. I'll leave the rest for you to do for practice. But I want to jump down now and look at the next box. Okay, so you have some important terms, label on the above examples, and then there are some more examples below: hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine. So let's look at a few of those, then we'll go back and label those terms on the examples that we used. So first I want to look at, I'll leave hydrogen for you to do, H2, you can handle that. But let's look at N2. Okay, so N2, I have 2 nitrogens. So I have nitrogen is in group 5A. So I have 5 plus 5. That's 10 electrons. Okay, so I draw the skeletal structure. There's only one way to do it. 2 nitrogens by each other. So now I have 8 electrons left over. So I use 2. Okay, so 8 equally divided between 2 atoms would be 4 each. 1, 2, 3, 4. 1, 2, 3, 4. So now I go back and double check myself. I use 2, 4, 6, 8, 10 electrons together, so I'm good. Each nitrogen has 2, 4. Nitrogen only has 6 electrons each here. So that's not right. So there's no other place to put these electrons. So if I can't make the answer work out correctly by placing electrons, what was my next option? Yeah, multiple bonds was my next option. So let's try this. What if I did nitrogen with 2 bonds between it? Okay. So then I have 10 electrons originally minus 4. So now I only have 6 electrons left over. So now I would put 3 around each. So if we put 3 electrons around each nitrogen has 1, 2, 3, 4, 5, only 7 valence electrons each. So we're still not right. So let's try a triple bond. So I start off with 10 electrons. I've already used 6, so I only have 4 left. So let's put 2 around each nitrogen. So now let's double check. I used 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, so I'm good there. Each nitrogen has 1, 2, 3, 4, 5, 6, 7, 8, so we're in good shape here. So this is the Lewis structure for nitrogen, N2, diatomic nitrogen, okay? So you see it's kind of a trial and error game. If it doesn't work out originally, use your last resort, multiple bonds, okay? So let's try the next diatomic molecule or diatomic atom, O2. So O2 is in, or oxygen rather, is in 6A, so I have 6 plus 6 is 12 electrons total. So I start off with a skeletal structure. I've used 2 electrons, so I'm left with 10. So I'll put 5 around each. So typically, if you ever have an unpaired electron, something's probably wrong, okay? That's very rarely going to be the case. So that's not correct. We see that each oxygen does not have the 8 electrons that it needs. So we try our next option. We try double bond. So I started off with 10 electrons. I just used 4. So now I have 6 left. Or excuse me, I started off with 12, I apologize. You started off with 12 electrons originally. So 12 electrons, I just used 4. So now I have 8 electrons left to use. Okay, so I put 4 around each oxygen. 1, 2, 3, 4. 1, 2, 3, 4. So now I go back and add up the total. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So I'm good. And each oxygen has 8 electrons around it, so it's good there. So go ahead on your own and draw out the Lewis structures for the remaining diatomic atoms there. You'll see that the rest contain only single bonds. The nitrogen and oxygen are the cases there where you have double and triple bonds. So that's definitely not something you would have to memorize, okay? That's something that we can find out each time we draw Lewis structures. There's no point in memorizing what compounds have double bonds, what have triple bonds. That's pointless. There's millions of compounds out there. But we learn how to use these steps so that when we're faced with a compound, we can draw it out correctly, determine how many single bonds it has, how many double bonds it has, and then we want to figure out how many lone pairs of electrons are on each atom, okay? So let's go back up between the 2 boxes in the notes and let's label some of those terms that we have listed out in bullets there. Okay, so let's go through and label some of the terms that were listed out in the notes there that you should be able to apply. So first let's look at a nonpolar covalent bond. So a nonpolar covalent bond we know is a covalent bond where electrons are shared equally, okay? So we think about the electronegativity differences that have to be present to have a nonpolar covalent bond. So we know the range is between 0 and 0.4 for the electronegativity differences for nonpolar covalent bonds there. So we know hydrogen and hydrogen have the same electronegativity. So this would be an example of a nonpolar covalent bond. Or I could circle the whole molecule and say a nonpolar covalent molecule. So then if I look at, let's look at this one, nitrogen and hydrogen. So nitrogen has an electronegativity of 3.0, hydrogen is 2.1, so the electronegativity difference is what did I say there? I'm sorry, 3.0, 2.1, so 0.9. So this would be an example of a polar covalent bond. So the electrons are being pulled towards the nitrogen. So hydrogen is slightly positive, nitrogen is slightly negative there. So we could go through and label all these as polar or nonpolar covalent. This one's a little bit different. You might get something a little bit strange for that answer. So don't worry about labeling this bond as polar or nonpolar covalent. Just be able to do that if you were ever asked to for any bond that you get using the Pauling electronegativities. So the next term it asks you to apply or label are lone pairs. So that's a lone pair, that's a lone pair. So anytime you have a pair of dots, that's a lone pair. So multiple bonds, so triple bonds and double bonds are multiple bonds. So that's a double bond, that's a triple bond. So those are both categories of multiple bonds. So we call those double covalent or triple covalent bonds. So everything else is a single covalent bond. So single covalent bond, single covalent bond. So all of these Lewis structures we could call structural formulas. They show the structure of the atom. We could also say they are molecules. We could also say they are molecular compounds because they only contain covalent bonds. Chemical formula, that's something like this, the SiF4, It tells you the number and type of atoms. And then lastly, we have diatomic molecules. Remember, the diatomic molecules are hydrogen, nitrogen, oxygen, fluorine, bromine, iodine. They are a molecule made up of two of the same type of atom bonded together. So I can circle that as being a diatomic molecule, that, or that as well. Okay? So obviously you won't be asked on every example to label all these terms. Just be sure you're familiar with these terms and can apply these terms if you ever are asked to. So hopefully this made the rules for writing Lewis structures or drawing Lewis structures a little bit easier. These are the more simple examples. So we've started off. Notice all of these atoms that we've discussed in the video, except for hydrogen, obeyed the octet rule. There were none of the strange exceptions. So hopefully you're comfortable drawing the more simple Lewis structures now, and we can move forward to some of the molecules that have a little bit more of a complex Lewis structure. So sometimes they don't obey the octet rule. So we'll look at that in the next video.